Hello everyone, my name is Alessandro Cultrera. I am a researcher at the Italian National Institute for Metrological Research, and I work in electrical metrology. Today, I will give you the first part of the video tutorial about electrical resistance tomography. Let's begin with a crash course on electrical resistance tomography. In brief, to implement this technique, typically you need a fixture to contact your sample, so a fixture with a number of contacts, boundary electrical contacts that can land or can be fabricated on your sample. And these contacts must be wired with a multiplexer or some kind of switch that allows you to implement different measurement configurations. This switching unit will be connected to a current source and a voltmeter. With this setup, you can perform the 4-terminal electrical resistance measurements. The way you perform these measurements, it's called stimulation and measurement protocol. And typically, the so-called adjacent protocol is used, where each pair of adjacent contacts are used once as current source pair, and all the other contacts are used for voltage sensing. Then the protocol involves a number of these measurement configurations in order to get the most possible independent information of the electrical network represented by your sample. Next to this, you need to feed this information to a numerical method which can solve an inverse problem. So the problem of having the one-dimensional information about your electrical resistance measurements and retrieve a reasonable conductivity distribution, which is a two-dimensional object, which represents the distribution of conductivity of your sample. So in practice, consider having a graphene sample or a thin metallic film sample of what you want to check the uniformity of the conductivity. You can place this sample in a suitable sample holder fixtures provided with electrical contacts, and at the end of this process you get a conductivity map representing the distribution of conductivity over the sample area. Just a little bit of history from where it comes, electrical resistance tomography. So initially, probably the first scientists who considered to perform kind of resistivity measurement of objects, in this case the Earth, the ground, was Robert Fox. Robert Fox in 1830 thought that it could be possible to exploit the spontaneous polarization phenomena on the ground to assess the conductivity distribution and probably to get insight of the presence of minerals of different kinds. Later, at the beginning of the 19th century, the Schlumberger brothers performed this kind of measurement with a little more sophisticated means. So it was a first kind of electrical resistivity measurements of the ground. But the first rigorous implementation of a 4-terminal resistance measurement in order to assess the resistivity of the ground was by Frank Wenner. In fact, Wenner published a method for measuring the Earth resistivity in 1960. The method required a current source and a voltage sense. Exactly what we do now in established 4-terminal resistance measurements that we applied here for electrical resistance tomography. So at the beginning of the 19th century, 4-terminal electrical measurements were used to get insight of the Earth conductivity. But this could just give an idea, a better idea of the scenario underground. Until the problem of regularization was solved. In fact, Andrei Tikhonov in 1943 published its own theorem about regularization of ill-posed inverse problems. And this allowed indeed to get inside of the actual distribution of conductivity of a mean of an object, in this case the underground, from the information contained in the four-terminal resistance measurements. So let's talk about the implementation of electrical resistance tomography. For example, our experimental setup is based on a current source, a voltage sensing instrument, voltmeter, a switching matrix, a switching unit to perform the different measurement configurations. Then there is data acquisition based on a PC, and the sample holder, the fixture that provides the contacting. As you can see, the sample fixture allows you to contact 1 by 1 centimeter samples on rigid substrates with 16 contacts, which are spring-mounted tips with a small diameter, so that can be considered point contacts. Once the sample is hosted by the fixture, the contact lands and act as a purely mechanical contacts on the samples. All these contacts are wired to the switching matrix in order to perform the different measurement configuration required by the stimulation and measurement protocol. All these measurements are four-terminal resistance measurements. But wait, in principle, this technique allows you to perform and include also the two-terminal and the three-terminal resistance measurement. But for practical reasons, it is enough to consider the four-terminal resistance measurements. Why? Because with four-terminal resistance measurements, you get rid of the series resistance of the contacts themselves and the series resistance represented by all the connections and the relay and other components of the measurement chain. So, for example, when you perform a two-terminal resistance measurement, you include in your measurements both the resistance of the sample and the resistance of the contacts. With the four-terminal configuration, you use two contacts to inject the current, no matter the voltage you need to inject this current, which depends on the contact resistance. Then, with another pair of contacts, you sense the voltage. The ratio between the injected current and the sensed voltage using these four contacts allows you to measure just the sample resistance. Electrical resistance tomography is not the only technique that uses four-terminal electrical resistance, obviously. There are more established techniques that makes use of this approach. For example, the four inline point probe technique, which requires four inline contacts, two of which used to inject the current and two of which used for sensing the voltage. With numerical factors derived by theorems, you can get the sample sheet conductance or sheet resistance just by performing this measurement. On the other side, the so-called Van der Poel method requires four contacts, but no more inside your sample, but at the boundary of your sample. And with two dual resistance measurements, four-terminal measurements, it is possible again to get a global estimation of the sample resistivity, sheet resistance, in case of thin films. You can think about electrical resistance tomography as an extension of these more established techniques. Electrical resistance tomography requires a larger set, compared to Van der Poel method, of four-terminal resistance measurements. This redundant information acquired from the boundary of the sample allows you to retrieve not only a global estimation of the sample resistivity, but also, by means of numerical methods, which will be discussed in the part 2 of this tutorial, to get insight of the conductivity distribution over the sample. Let's now take a look to some examples of results of electrical resistance tomography applied to thin film materials. In this example, we consider commercial chemical vapor deposition graphene samples which have been mapped by electrical resistance tomography. As you can see, the sample look transparent, so optical techniques maybe are less indicated for this kind of investigation. Instead, electrical resistance tomography, just by performing these boundary measurements without touching the interior of the sample, which is a monolayer structure, so very fragile, can get insight of the conductivity distribution of the sample. You can see a map obtained with ERT, with electrical resistance tomography, and by comparison, we used a completely different technique, which also has already been subject of standardization, so it's a more established method in this sense. This other technique is the terahertz time domain spectroscopy. Terahertz time domain spectroscopy uses a focused beam of infrared light, and the reflection and transmission coefficients that can be measured allows you to perform an estimation based on the Drude-Smith model about the conductivity, the local conductivity of your sample. So we perform this comparison in order to understand how much electrical resistance tomography was reliable on this kind of sample. Another example of application of electrical resistance tomography to nanostructured materials is represented by the investigation of metallic nanowires. In particular, these metallic nanowires create an interconnected network of these very small silver-based sticks, which have so-called memoristive properties. This means that the resistivity of the junction between one stick and another, one nanowire and another, can be tuned by applying a suitable voltage. So the conductivity distribution over a network of memoristive nanowires can be tuned and also can change over time. So electrical resistance tomography in this case allows you both to map the so-called pristine state of your sample, so the initial state of your sample. Then, using suitable applied voltage through pairs of the same contacts available for electrical resistance tomography, using suitable applied voltage, the network can be stimulated in order to get a specific potentiation of the conductivity of the network, and then the very same technique can be used to monitor the evolution in time of this potentiation of the network of metallic nanowires. Moreover, this potentiation and monitoring can be performed on the same sample more times along different directions in this example. So in this example, you see that this technique is minimally invasive but also minimally destructive, and can be used to perform characterization and monitoring of the evolution of thin films and 2D materials and nanostructured materials samples without altering the condition of the sample if not desired. So, in this first part of the tutorial about electrical resistance tomography, I gave you an insight of the origin of the technique, its derivation from more established multi-terminal measurement techniques, and some example of application to novel materials, and this concerning the more experimental side of the problem. Now you are welcome to follow the next part of the tutorial.